Hello students, welcome to the class of Control System 2. I am Priyanjali Mukherjee, Assistant Professor of Electrical Engineering Department of Narula Institute of Technology. Today this is our first video lecture and today's topic is the Introduction to State Space Representation. This video contains the introduction, the state variable, necessity of state space approach, the input-output versus state variable models, the state variable equation, the block diagram of state space model, the example, reference and the MCQ questions. So let us introduce the state space. In the previous semester, we have considered the analysis and performance of the control systems based on the transfer function model and graphical approach. The graphical approach means it may be the Bode plot or root locus and the Nyquist plots. And these are called the conventional approach. Now, these methods we have modeled earlier the system in the form of the transfer function. So that means the overall mathematical model, that is represented by the differential equation, and it can be divided into two domains. One is in the frequency domain technique and another is the time domain technique. And these two approaches for the analysis and design of control systems. So the classical technique or the frequency domain technique are the transfer function models and the graphical plots like the Bode plot, root locus, etc. And the modern technique or the time domain technique is the state variable approach. Next is the state variable. What is the state variable? Now there are some terms associated with state variables of the control system. So first one is the state. Now the state of a control system at a time t equal to t0 is the smallest set of variables which called the state variables, and such that the knowledge of these variables along with the knowledge of the inputs at t is equal to t0 is sufficient to determine the output dynamics of the system at any time that t may be greater than t0. So state is a group of variables which summarize the history of the system in order to predict the future values or the output of the system. Or in other words, the state of the system represents the minimum amount of information which is required to know the system at t is equal to t0 so that the future behavior can be determined with the reference to the input before t0. Next is the state variable. Now the state variables of the dynamic system are the smallest set of variables that determine the state of the dynamic system. That is, the state variables are the minimal set of variables such that the knowledge of these variables at any initial time is represented by t is equal to t0, and these variables at any initial time together with the knowledge of the inputs for t greater than equal to t0 is sufficiently to complete the determine the behavior of the system for any time t greater than is equal to t0. So the state variable is the number of variables required that is equal to the number of storage elements present in the given system. And the state variables need not be physically measurable or observable quantities. The variables that do not represent the physical quantities and those that are neither be measurable nor be observable, these also can be chosen as state variables. So there is some freedom in choice of state variables which gives an added advantage in the state space method. And generally, the nth order system is described by the collection of the n number of state variables. Next is the state vector. So if n number of state variables are needed to completely describe the behavior of a given system, then these n number of state variables can be considered as the n number of components of any vector. That means it is a vector which contains the state variables as the elements. So this vector is called the state vector, and state vector can determine uniquely the system state xt for any time t greater than is equal to t0. And once the state t at t equal to t0 is given, the input u for t greater than t0 is specified. So overall state space are considered the minimum number of state variables which are necessary to describe the dynamics of the control system, and the n-dimensional space whose coordinate axis consists the x-axis, y-axis up to xn axis is called the state space. For two-dimensional cases, the state space reduced to the state plane or the phase plane, and any state can be represented by a point in this state space. So next is the necessity of the state space approach. So basically, in the previous cases, we have considered the conventional approach, and all these methods which we have done earlier, we modeled the system in the form of the transfer function. And the transfer function approach has some limitations. So let us check what are the limitations of the transfer function approach. So firstly, during the analysis by the transfer function approach, we have considered the initial conditions are 0. And as we consider the initial conditions, so it gives us the more precise response. So consideration of all initial conditions associated with the system in the state model gives us a major advantage. Next is the transfer function approach shows the inconvenience towards the analysis of MIMO system. That means it is only applicable for CISO system. So not only that CISO system, but also those should be the linear and time invariant. That means if a system is MIMO system or multiple input, multiple output, or the nonlinear system or the time variant system, then you cannot apply the transfer function model. Similarly, the analysis of system output for specified input is obtained, and no information regarding the internal state of the system can be measured in the transfer function approach. And it gives the analysis of system for some specific types of inputs which we have used, such as the step input, ramp input, etc. So state variable approach is associated with the matrix or vector modeling, and it can be considered as an efficient computational approach. Next is the input-output model versus the state models. So the state space model is considered in the time domain, whereas the input-output or the transfer function model has been considered in the frequency domain. And in state space model, we include the initial condition, and input-output model or transfer function model, we do not include the initial condition. We always assume all the initial conditions are 0. In state space model, we can apply this state space model to the linear time invariant linear time variant as well as non-linear system. But the transfer function model has been restricted for the linear time invariant system. And when we are going to write the state space model, it can be written on the first grade ordinary differential equation. An input output model is good for analyzing the frequency response. And the state space model can be applicable for the multiple input multiple output system, whereas the transfer function model is only applicable for single input single output system. So these are the differences between the transfer function model and the state models. So next is the state variable equation, which one is very important for the state analysis of the control systems. So the system equations which can be written in the form of first order differential equations in time domain are known as the state equation. So the state equation is x dot is equal to ax plus au and y equal to cx plus du is the output equation. So the number of state equation and the state variable is equal to the order of the differential equations required to model it, and we can rewrite the equations for time varying system with the coefficient a and b, and a and b are not constants but are the function of the times. So in this equation we can see that the x is the state vector, x dot is the derivative of the state vector with respect to time, and this x dot is equal to ax plus bu is the state equation where a is the system matrix and b is the input matrix. Similarly, the output equation is y equal to cx plus du, where c is the output matrix, x is the state vector, y is the feed forward matrix, and u is the input vector. So A is actually called the system matrix, B is called input coupling matrix, C is the output coupling matrix, and D is the input output coupling matrix. And the term du indicates the direct coupling of the input to the output, and the direct coupling of the input to the output is rare in the control system. So generally we got that D equal to 0. And the state equations and the output equations are called dynamic equations of the system, and these are also known as the state model of the system. Next is the block diagram of the state space model. So the dynamics of the control system may be described by the first order differential equation, and the differential equations can be diagrammatically designed using the integrators, summers, constant multipliers, and in the form of block diagram. So the integrators are shown here by a box, and the sign of the integration can be put inside the box, or we can write 1 by s inside the box, which represents it as an integrator, because Laplace transform of the integration term is 1 by s. So we can write 1 by s, or we can put the sign of the integration in the box, or it may be triangle in some cases. So here we can see that is ut is given input and yt is the output. These are the summing points or the summers, and this one is x dot t. So if we use x dot t, then it can after the integration it becomes xt, and the equations are x dot t is equal to a into x plus b into u. So from x we are giving the a feedback, so a into x plus b into u. Similarly, the y is equal to c into x plus d into u. So this model can represents the state equation as well as the output equation, and this one is the block diagram representation of the state model. Next is the example. So here one example is given, a mass spring damper system. So first we need to identify the system equation, and here we can see it can be represented by my double dot, because y is the displacement, plus by dot plus ky, that is equal to f of t. So the system is of the second order. That means there should be involved two state variables or the integrators. So first we will define the state variables. So first we are assigning the state variable x1, that is equal to y, and x2, that is the y dot, and y dot can be written as x2. So x1 is equal to y, x1 dot is equal to x2, that is equal to y dot. So x2 dot will be y double dot, and from this system equation we can write that y double dot, that is equal to 1 by m into minus b y dot plus ky minus 1 by m into f of t. Now we can put the values of y dot in this equation. So we are getting minus b by m into x2 minus k by m into x1 minus 1 by m into f of t. So we are getting two equations. First one is x1 dot is equal to x2, and the second one is x2 dot equal to minus b by m x2 minus k by m into x1 minus 1 by m into f of t. So these two are the equations, and we will write the state equation and the output equation from these two equations. So we know that the state equation is x dot t is equal to a of x plus b of u, and the output equation equal to y is equal to cx plus du. So here we will write the x1 dot and x2 dot in matrix form, and as it is a 2 by 1 matrix, and a should be is equal to 2 by 2 matrix, plus b will be equal to 2 by 1 matrix. Actually, if A is n by n matrix, then B should be equal to n into 1 matrix, C will be 1 by n matrix, and D will be a constant, and U is the scalar or the control variable. So here x1 dot is equal to only the x2. So the coefficient of x1 term will be 0 and x2 term will be 1, and input here is the ft, because we are giving the force over here, and due to this force the displacement is happening. So that's why y is the output and f of t is the input. So f of t is input, so the term x1 dot can be written as 0 into x1 plus 1 into x2 plus 0 into ft. So it becomes x1 dot is equal to x2. Similarly, for the x2, we will rewrite the coefficients of x1 and x2 in their places. So x1 coefficient is minus k divided by m. So that's why it is written here minus k divided by m. For x2, the coefficient is minus b divided by m. So here the term is minus b divided by m, and plus f of t. The coefficient of f of t is minus 1 by m. So it can be written as minus 1 by m. So this 0, 1 minus k by m minus b by m is actually represents the system matrix or the A matrix. Similarly, the B matrix becomes 0 and minus 1 by m. And finally, the output equation. Output is y, because due to presence of this force, the displacement is y, so output will be y, and output is equal to x1, because we have defined the state variables in this manner. So y is equal to 1, 0, x1 into x2. So it represents y is equal to 1 into x1 plus 0 into x2, and there is no d term because d term is 0 over here, and as earlier we have discussed, the direct coupling of the input to the output is rare in the control system. So here also you can see the d is equal to 0. So in this way we can draw the state diagram just like the earlier. So here ft can be given as the input, so the u will be represented by f of t, and minus 1 by m, so the gain of this system is minus 1 by m, and there is two variables, one is x2 dot and another is the x1 dot. So here it is x2 dot, and after first integration it will be x2, and similarly again x2 dot, x2 is equal to x1 dot, so after the again next integration the output will be x1, and we know that x1 is equal to y, which is the output of the system. And x2 dot is equal to, you can see from here, x2 dot is equal to minus b by m into x2 minus k by m into x1 into minus 1 by m into ft. So that's why from x2 we are drawing a gain, that is b by m, and similarly from x1 we are drawing another gain, that is k divided by m, and both are summed up here, and then we are taking the minus sign over here. So the x2 dot becomes 1 by m into f of t minus b by m into x2 minus k by m into x1. So this feedback path has been completed, and it represents the state equation. And the output equation is y is equal to x1. So y is same as the x1. So this represents the output equation. So in this way we can describe the system by the set of the first order differential equation, and then we can represent it diagrammatically by using the integrators, the summing points, the constant multipliers, and we can form the block diagram of the system. These are the references. I hope after this video lecture you have a clear idea about today's topic. Now we will go through some question answer session in context of this video lecture. So you are requested to go through it gradually and solve the questions by your own. The answers are attached at the end of each question.